So today I want to talk to you about some machine learning algorithms that are really not much discussed. For example, we talk a lot about how to work with text, for example, right? So, for example, if I have some text and I want to predict maybe the next word or something, and those are large language models, for example, that we see a lot out there. Maybe I'm interested in comparing images, right? For example, let's say this is a dog. This is my very good impersonation of a dog. And this is, let's say, a cat. And then I want to predict, is this new image a dog or a cat? We also have a lot of algorithms that work with tabular data. So like in a table, and I want to find out whether this person maybe is eligible for a loan. But how do we do exactly the same thing, but with graphs? So here are two graphs that I will show to you. I have graph G1 and graph G2. This graph has 6 nodes, so these colored blobs are called nodes, and the connections between them are called edges. In this particular graph, the nodes have color, so they can be red or blue. And there are 6 nodes with 1, 2, 3, 4, 5, 6 edges as well. And we have a second graph, which kind of looks maybe similar. It also has 6 nodes, with the difference that I have 3 blues here rather than 2, and the connections here are a bit different.
They kind of look like molecule maps. Are the colors important? The differences in colors?
That's awesome comment. I was gonna exactly discuss why do we do these things? And molecules are the best example. So maybe if you have something that looks like a molecule, like a carbon connected to an oxygen that's connected to a hydrogen, and this keeps going. I'm not a chemist, so I don't know how this is gonna go, but I could think that maybe I will represent a carbon with a red blob and an oxygen with a blue one. For the chemists out there, this is probably not a real molecule, but we don't care. But you could absolutely model molecules as graphs. You could model other things. You could model friendship networks in which colors maybe represent people's preferences about a certain topic, or something that identifies them in some way.
So these are obviously graphs in a kind of true sense of the word, with nodes and edges. We're not looking at plots here.
Yeah, not plots. And that's the first important distinction that we should.
But could you do plots like this as well, or is that different?
For what we're going to see today, plots cannot be analyzed with the same algorithms. What we're going to look today are very specific to graphs in that sense of nodes and edges. Network is a way to describe them. A network is a way that you maybe differ the graphs and the plots.
These actually could be parts of a cloud or something, couldn't they?
They could. Actually, they could be knowledge graphs that I know you discussed in the channel before. They could be anything that you can represent with connections. Maybe it's a natural question that we have. Maybe you have a third graph that I'm going to draw here. Maybe this third graph looks something like this. Right, so here I have a third graph. I'm calling it very creatively G3. And you can see it's a bit different from G1 and G2. It also has, unlike the other ones, it has 1, 2, 3, 4, 5, 6, 7 nodes instead of 6, again. Sean, maybe you can tell me reasons why G3 should be more similar to G1, and maybe reasons that it should be more similar to G2.
So obviously I'm looking at it upside down, but that probably shouldn't matter actually.
It doesn't. Very good.
But looking at the G1 to G2, you've got that kind of triangle at the top from where you are. But then it feels like G1 to me because it's just maybe an extension taking those 2 blues to be 3, and it feels more like that to me than G2.
And there is this kind of things coming out of it, which here we have 2, but with an extra one. So maybe kind of these parts are sort of similar. On the other hand, this part is very similar to this one, it seems.
Oh yeah, the other way around, of course,
right?
Yeah.
But it's upside down. But again, maybe we don't care about this. Of course, these are toy examples, right? These are like not realistic examples. But maybe in real life, these are molecules, again, coming back to the example. And maybe this G1 belongs to a big group of molecules that somehow are good. They are drug that solves your problem. They are active or something. And these are not good or inactive. You may want to come up with a new one and say, should this belong to group 1 or group 2? So before actually going there and then doing the synthesization of them, could I maybe have models that will tell me it kind of looks more like this, looks like this. So today, we're going to see two very, very, very simple models that nonetheless are going to give us conflicting answers. And the reason why they give conflicting answers is to highlight the fact that working with graphs is really hard, and we're never expected to have one final only way of doing things.
Because there are presumably all sorts of different ways of saying they're similar, you know, how many edges, what different colours, how many, you know, how do you measure it, I suppose, is the question, isn't it?
And you've touched on something that's quite profound. So if you have two vectors, and maybe two vectors like this, and they have numbers, like there may be 1, 2, 5, and 7, and the other one is 1, 2, 4, and 7, you want to know if they are the same. It's very easy. You just walk from the beginning of the vector, comparing the entries. If they are the same, keep going. If they are different, you know the vectors are different, and you are done. That can be done in linear time for those of you who like complexity of algorithms. Graphs, not that easy. The graph isomorphism problem is not known to be solvable in that quick way. So the whole point is that we can't even tell if graphs are the same. So let alone the degree of similarity that they have. That's exactly what we're going to calculate, degree of similarity, but it's not an unique answer. And maybe if there's one takeaway of this whole video is that when we do such similarities and comparison between graphs, we throw information away. What we throw away and what we keep is the magic. So if you're applying this to some sort of application, some specific application, you may want to discard some information. You may want to keep some other information. And that's the important choice that you would have to make. We start with an algorithm called vertex histogram. You probably remember histograms from maybe when you studied statistics. So if I would look at G1, for example, and I want to maybe count, so histogram is merely here counting the number of occurrences of a given color label in that case. So for G1, I'll have 2 blue ones and 1, 2, 3, 4 red ones. So this is my histogram for the first graph. I will not draw histograms as plots like this. I'm just going to draw vectors. So that's going to be quicker, I think. So I'm just going to get blues. Oh, God. Okay. Reds. And we're just going to calculate. I'm going to call them VH for vertex histogram, in this case of G1. So this is going to be a vector that has 2 blues and 4 reds. And then vertex histogram of G2. What happens? Well, I have 3 blues here and 3 reds. So this is going to be a 3,3. So you see what I'm doing? I'm suddenly creating a vector that sort of represents the graphs. Now, you're probably thinking there are many things that we're discarding with this that we're going to analyze later. Okay, so at this point, you could get these vectors, put it to a nice Cartesian plane, place them there, and do your favorite algorithm. Of course, this is a toy example, but imagine that you have hundreds and hundreds of those points. You could use nearest neighbor classifier. You could use anything that you want. We are going to use something called kernel methods. We're not going to get into the details of the kernel methods, but we're going to go just see one example of how they work. So if I want to use the kernel method, I will take the inner product between 3 and 1 and 3 and 2, because I want to compare 3, right? So at this point, I don't want to compare 1 with 2. I just want to compare 3 with both of them. So we're going to go through step by step. So if I do the inner product is going to be 2, 4. If you have not done inner products or dot products before, you can it's just a sort of a multiplication of vectors in such a way that you multiply entry by entry and add them together. So in this case, I do 2 times 4, which gives me 8, plus 4 times 3, and that's 12. So this would be 8 plus 12, and that gives me 20. If I do the same thing with G2 now, and G3, I'm going to get, we don't have to write it down, we can just look in here, it's going to be 4 times 3, 12, plus 3 times 3, that's 9, which gives us 21. Right, inner products are a good measure of similarity between two things, two vectors. For the purpose of this particular part of the algorithm, we can conclude that G3 is more similar to 2, because 21 is more than 20, than to G1. You're probably thinking many things at this point, because you'd be like, well, I can come up with so many examples of things that shouldn't be similar, but give me a high number here. And that's absolutely true. I mean, I will give you many. If you just have one vector that has huge numbers and the other one has low numbers, this product is going to be high. Maybe higher than the comparing it with itself, which should be the utmost similarity. But nonetheless, inner products are understood as measure of similarity, and especially because we are going to use algorithms such as SVMs, support vector machines, in which inner products play a very central role in comparing and creating the boundaries between the classes and everything. If you are really bothered with the fact that these numbers are very high, or that you could get similarity that's much higher than you would like otherwise with outlier numbers here, you can always normalize your vectors. Now, it depends on your application. Maybe normalizing does not make sense. Maybe normalizing does make sense. So again, it really depends on the particular algorithm you're using. Okay, Sean, there is a central piece missing in whatever I've done here.
It's the edges, isn't it?
Exactly.
And what they're connected to, not just how many there are, but where they are and all of that sort of stuff.
Awesome. Actually, not even how many there are at this point, we are completely ignoring. We're not taking into account edges at all. Nonetheless, this is a very simple example that I like doing because it gives us a flavor of what's going on. There's one thing that may be bothering you. Does it mean that if you put this in a support vector machine algorithm, the fact that 21 is higher than 20 would automatically be the case that G3 is classified as the same group as the G2? Not necessarily. Support vector machines work with lots of different parameters, and there are biased terms and all sorts of other parameters and factors that should be taken into account. But nonetheless, the measure of similarity still works. So the higher the number, the more similar. It's sort of the opposite as distance, where the higher the number, the more different. Now we're going to get edges into the whole thing and see what happens. This is called Weisferler-Lehmann algorithms. In this case, we're going to do the graph kernel version of them. They show up in other parts of graph theory. What we're going to do, and the basis of what we're doing now, is the following. Look at this, for example, this red node and this other red node. They are similar because they're both red. But they are also similar in the sense that they have only one neighbor that happens to be blue. So they are not only the same color, but their neighbors have the same color. Unlike, for example, this one and this one. So the top one here is red, but actually neighbors are red and a blue, whereas this is red and neighbors are blue. So for the purpose of this algorithm, now we're going to say that these two things are the same, but these two things are not the same anymore because their neighborhoods are different. We're going to analyze all the patterns that we see in this particular graph. I'm now writing WL, and I'm putting a number 1. You may guess why 1 is in here at this point, but we're going to discuss later.
Is that for one neighbor?
It's not from one neighbor. I'm going to give you a spoiler. It's I'm only looking at immediate neighbors. So I'm looking only at neighbors...
With distance 1.
Distance 1, exactly. So you can guess that WL2 is going to somehow look at neighbors of neighbors. So the first pattern that I'm going to analyze is the one we just discussed. So it's a red, comma, and I'm adding a comma here to clarify that the first red is the actual node's label, and what comes after the comma is the color of the neighbors, because you could have more than one. So it's red, comma, blue. Again, we're going to do a histogram again, but with the new patterns. So how many in the first graph have that behavior? So this one is a red with a blue one. This one is also red with a blue neighbor, but the other two are not the same. So there are two.
Oh, that only have one red. Yeah, got you. Okay.
Take out one red with a blue neighbor. Okay, but if you go to second graph, it seems that there is only one here, right? This one is a red with a blue neighbor, and the other reds, they have reds as neighbors, so they shouldn't be the same pattern. So we have a 1 here. Now, for G3, I have 3 actually, right? Because I have this one, and this one that are reds with blue neighbors. So it's going to be a long vector, longer than just 2, because now all the intricacies are being taken into account. And so not to get lost, because this can be confusing, I'm going to tick all the nodes that I've already processed in a way. If you actually want to implement this, there are smarter ways of doing it. You use hash functions and you're going to use all sorts of things. So let's get this thing done and then let's see what's happening. At this point, we've ticked all the nodes in the first graph. So we know that the rest of this feature vector here will have a bunch of zeros in the first line because there's no more patterns to pick up. Also, you probably realize that 2 plus 2 plus 2 is equal to 6, and as it should be, because each node will contribute to 1 tick in here. The second one will also have to add up to 6, and the last one will have to add up to 7, because I have 7 nodes. We seem to have some feature vectors going on. You can see there are a bunch more zeros now, because there are many patterns that we only find in 1 or 2 of the graphs. And if you have done machine learning at this point, you probably realize that something that is potentially starting to happen here is called overfitting. As we get more and more detailed on the type of patterns we get, it could be that we are too focused on the very, very, very fine details of our training data and we fail to generalize. So when we see something new, everything is different. So how much of this fine graining you do depends on, again, the application you want, and depends on, again, on things that you want to do. You may think that, for example, this will never be used, the vertex histogram one, because it disregards all the edges, right? So why would we use it? Nonetheless, it can be a baseline for your model. Let's go back to here and finalize our calculation. So we're taking the inner or dot products between these two things. So what happens if I do WL1 of G1 with WL1 of G3? I'm not going to rewrite the whole vectors down. We can just look here and see what's going to happen. So this first product is going to be 6. But it so happens that every other product is going to be 0, because 2 times 0 is 0, 0, and then 1.0, and 0, and 0, and 0. So the inner product, so the similarity using this algorithm in this case is 6. I should mention at this point, many implementations don't have just this vector here, but appends, so concatenates the first one, the vertex histogram at the beginning. So I would have something like 2, 4, the rest. And in that case, I would not get a 6, I would get 20 plus 6. But for this example, let's just stick with the second half. And finally, I can do WL1 of G2 and compare with G3. And then I get 1 times 3, which is 3. Then 1's with 0, and that's 0 again. And there's a 1 here, and there's also another 1 here. So I get 3 plus 1 plus 1, which is 5. Again, this is a measure of similarity that has a lot of caveats in it. It's not exactly a final say of everything, but it's just an example to see how, in this case, G3 seems more similar to G1, whereas before, it would be more similar to G2, because it was a 21 versus 20, and in this case, we have a 5 versus 6, or 6 for the first one.
But obviously, there's only 1 in it for both those examples, isn't there? I mean, they're very similar. They're just all very similar, right?
They are. It's just 1, and it's a very tiny difference. Again, doesn't mean your support vector machine algorithm is going to do it. We have not discussed exactly how these numbers go into your algorithm. For those of you who know kernel trick, it has to do with that. It has this idea that you do not need necessarily to know the feature vectors in order to do your prediction. In real life, you would not have only 3 graphs, you would have many, many, many more, and you will train in many more of them, and you test in some others. So this is just a toy example. If you actually implement this as SVMs, I do think for the first one, this is going to be classified as closer to G2. But again, there are bias terms involved, and the number is not predictive necessarily of what's going to happen. But it's just to get a feel of how these things are working. The kernel matrix that's going to come out of this for WL1, which we're not going to go into detail, is going to be something like this, that if I compare graph 2 with graph 3, which is this one, I get a 5. So I also get a 5 here, and I get a 6 if I compare 3 with 2, and I can fill these other numbers. So the magic happens because in support vector machines, for example, you can just put this matrix into the algorithm and get your predictions. So you don't necessarily need to know this thing. There are many graph kernel algorithms that actually don't ever do this because maybe those are infinitely long vectors. But nonetheless, you can get a number, and this number is going to be what you're going to use. There's one last thing we may be wondering at this point. You may say, well, okay, look at these two red nodes again. They're both red, they're similar. They both have a blue neighbor, so they're even more similar. But more than that, their blue neighbor so happens to have one red and one blue neighbor. So they're similar if I go up to distance 2, if you want. So the neighbors of the neighbors happen to be the same. Unlike these two, although they are both red and both have a blue neighbor, the neighbors of the blue neighbors are different because this one has a blue neighbor with a bunch of neighbors and this one has a blue neighbor with just 2 neighbors. So we can keep going, and we can keep going forever. So I could just create WL2, in which case WL2 would have patterns that would look a bit different. And at this point, you may be wondering, I am going to get lost, right? Where do I stop? Like neighbors of neighbor. Like, how do I even write it down? Okay, so that I pre-drawn this because it can get really complicated. So each pattern that we saw before will have a new color. So if it's red with a blue neighbor, like red with a blue neighbor is going to be this one, and this is now going to be pink. And this is going to be pink as well, and so on and so forth. So if you want to do WL2, you're going to look at patterns such as like pink, light green. And that's going to be like this one and this one, but not this one, because this is a pink with an orange as a neighbor. We do this to make sure we can do this whole thing efficiently, computationally speaking. Nonetheless, you can try to understand in an algorithm, if you use the feature vectors as we have them before, as 2 and 4, instead of the numbers that you get from the kernels, you could just do this, this algorithm with the vectors, try to explain, using some models to explain which feature was more important, and then try to bring out and say, this particular graph was deemed similar to G1 or the whatever class because of that pattern. So you could try to explain decisions as well using that. But that's another topic.
An edge or relationship like is located in. So Bush House is located in London. You see how
responsible for any behavior of autonomous
the
cars.
graph actually
Because how could they? They are completely distracted by the Computerphile videos. They're not even looking at the road.